Hello everyone, this is the third video in our special relativity series. Here we're going to talk about length contraction, another very interesting effect that happens in special relativity. Stay tuned until the end because you're going to solve a numerical example. So let's start with a relativistic length experiment. Okay, so we have a train car here. We have an observer B inside this car, and also we have this device right here. This device shoots light to a mirror, and it measures the time when the light comes back to the device. Okay. The distance between the device and the mirror is measured by this ruler here, LB, okay? And observer B is taking a look into this ruler, all right? Now, the second scenario, we have the same car, all right? But now it's moving at a constant speed u, all right? And we have an observer that's outside the train, which is observer A. Very good. We want now to take a look into the length of the ruler according to observer B and A. So let's start first calculating the time it takes for the light to hit the mirror and come back. Let's start with observer B, that's inside the car, okay? So we know that the time is the distance over the speed or the velocity, okay? Now the time that the light takes to go from the device to the mirror is LB divided by C, the speed of light, and the same time to go back to the device, okay? So it's LB over C. So the total time the observer B C, the total time he measures is 2 times LB over C, the time it takes to go and to come back. Okay, very good. Now let's go to observer A. Well, we know that the car is moving, right? So we know that this distance here is actually the distance of the ruler, okay, measured by the ruler from the device to the mirror, plus this displacement here of the car, okay? This displacement is given by u times TA, is the velocity of the car, times the time it takes to go from here to here. Okay, very good. So the time the light takes to travel from the device to the mirror will be LA, the distance measured by the ruler, plus this displacement here, because, well, when we shoot the light from here, it keeps going, but the car is moving, so it takes a longer distance, okay? So the time is this distance over C. Now the time to come back, well, it will be shorter, right? Because the light's coming from here, but the device is approaching the light because the car is moving. So the time it takes is the distance, which is LA, this distance, minus this displacement here over C, okay? Now let's keep going with some calculations. Alright, now what we want to do is calculate the total time for observer A. So let's do the same thing. The total time would be the time the light needs to reach the mirror plus the time it needs to go back to the device. But before adding these two times here, let's do some simplifications. Okay, so for TA1, we have we can multiply both sides by C, all right? Then we can put everything related to TA1 to one side of the equation, and we can factor this TA1 here. So we have TA1 times C minus U equals LA. Can keep going a little bit further and say that TA is LA over C minus U, and do the same thing for TA2. it will be exactly the same calculations, okay? But now instead of a positive sign here, we have a negative sign. Now that we isolated TA1 and TA2, we can just add them, all right? So the total time for A is LA over C minus U plus LA over C plus U. So here we can still do some other simplifications, okay? We can put this sum here to a common denominator, all right? So it's C minus 1 times C plus U, okay? C minus U plus times C plus U, okay? That's the common denominator here. We can put this LA, we can factor LA, also put it outside. And now we have this, the time for A is LA times this thing here. We can do some other simplifications. You see we have plus U and minus U here. So you just cut them out and you can multiply this factor, this multiplication here, okay? So you have that the time for A is LA times 2C over C squared minus U squared. All right, we can now divide everything by, we can factor this C squared here. All right, so it goes outside. We have 1 minus U squared over C squared. I'm leaving the equation like this just because of something I'm going to explain later, okay? From here, we can also do some simplifications, right? We can cut the C squared and the C over here. So we have that the total time for A is 2LA over C times 1 minus U squared over C squared. You can see that this part down here, it may remember you something, okay? I'm going to tell you later, but if you watched our previous videos on the special relativity, you may recognize this small part of the equation here, okay? But you can see that now that the time for B is different from the time for A, right? The only difference is this factor here related to the time, okay? Okay, so we can see now for A, if we increase the speed of light, okay, this becomes less than 1, so the time here becomes longer than the time for B, right? That's the time dilatation. All right, now from here we are interested actually in the length, right? So let's keep going. Good. So here we have the total time for B, the total time for A, and this is the expression from the previous videos on time dilatation, okay? We know that the time for A is the time for B over the square root of 1 minus U squared over C squared. That's the thing that's related to this expression here, okay? That's why I factored the C squared in this equation for the total time for A, all right? So here we are. Let's do some calculations to compare the length for B and for A. First, from this equation here, I can isolate the time for B, right? This is the relativistic time, so you can just isolate the time for B. And now we have that this is equals time for B, and also this is equal time for B. So well, we can put them together in one equation, right? From here, I can just isolate the time for A, which is this equation here. Now here again, I have that time for A equals this thing, and from our previous calculations, time for A also equals this thing here. So again, I can say that this equals this, right? And here we are. So time for A is this thing here. We can again do some simplifications, right? I can just cut this this number 2 right here, okay? And isolate LB. Okay, I'm dealing with this part of the equation here. So I divide everything by 2, both sides by 2, right? And I multiply both sides by this part here, so I have this expression, okay? Again, do some more simplifications. I can divide everything by this, okay? By the square root of 1 minus u squared over c squared. Actually, I'm factoring this this part here, okay? And I get this equation, LB equals LA over the square root of 1 minus u squared over c squared. So LA equals LB times this thing here, the square root of 1 minus u squared over c squared. So see how length is different depending on the observer, right? Depending on the reference frame you are in. You can see that this, when the car approaches the speed of light, this becomes closer to 1, okay? So this is actually less than 1, this part inside the square root, and the square root of a number that's less than 1 is another number that's less than 1 also. So it's a number less than 1, 0 point something, times LB. So you can see now that the length of the ruler for observer A is actually shorter than the length of the ruler for observer B. We are dealing here with a length contraction. Let's go through now an example, a numerical example that will make things clearer for you. So here we go, okay? This is the same example as before, but now we are adding some numbers, all right? Let's assume that the length of the ruler for observer B is 1 meter, and the car is moving at 0.9 times the speed of light, okay? Very close to the speed of light. And let's compare the length for observer B and A. So according to our previous calculations, the length for A is the length for B times the square root of 1 minus u squared over c squared. Okay? So now we can just add the values here. So we have that L for A is 1, the length of the ruler for observer B, times the square root of 1 minus 0.9c, that's the speed of the car, okay, 0.9c squared over c squared. Here we can cut out the c squared, you can see, right? So the length for A is the square root of 0.19, and this gives us that the length for A is 0.436 meters, which is pretty shorter than the length for B, right? So see that both lengths are actually correct, okay? You may ask, so what's the real thing that's happening, right? And again, the same thing as for the time dilatation, both lengths are the correct length. The only thing that changes is the frame of reference, if you are inside the car or outside, okay? In other words, the length depends on the frame of reference you are in. And when we approach speeds that's really close to the speed of light, see that the length changes a lot, right? So that's it for today. Hope you enjoyed and see you next time.
What did you think about this video? We appreciate your feedback, so tell us in the comments section.